All right, welcome. Today we are cracking the code on some of the most common and, frankly, most powerful chemical compounds you run into every single day, probably without even realizing it. We're going to dig into the simple but amazing chemistry behind alcohols, ethers, and thiols. So, to get started, we're not heading into some high-tech lab. Nope, we're actually starting with a bit of history, and it's surprisingly explosive. I know, it sounds like the beginning of a really weird riddle, right? But believe it or not, there's a single, super versatile family of molecules that connects all of these things. That's right. Way before we had fancy lab equipment, this was the go-to test. Sailors in the British Royal Navy needed to make sure the rum rations hadn't been watered down, so they'd pour a little on some gunpowder. If it still lit on fire, that was the proof that it was strong enough. Pretty clever, huh? And you see that exact same chemical property in action today, just with a little more flair. When a chef sets a dish alight, that's flambé. So what is it about alcohol that gives it this unique ability to burn, and so many other weirdly specific characteristics? To figure that out, we've got to zoom way in. We need to look at what an alcohol actually is, right down at the molecular level, because that's where all the magic is really happening. And here it is. The secret to basically everything an alcohol can do is this thing right here, the hydroxyl group. It's just one oxygen atom bonded to one hydrogen atom. But trust me, this tiny little addition changes the entire game. You see, that oxygen atom is kind of greedy. It pulls the electrons in the molecule closer to it. This creates a tiny negative charge on one end and a tiny positive charge on the other. And just like that, the whole molecule becomes polar. It basically acts like a tiny magnet, sticking to other alcohol molecules. And if you want to see what a huge difference that makes, just look at this. Methane, which is about the same size as methanol but isn't polar, is a gas all the way down to a freezing minus 162 degrees Celsius. But methanol, thanks to those strong magnetic attractions, we call them hydrogen bonds, it stays a liquid all the way up to 65 degrees Celsius. It takes way more energy to pull those little magnets apart. Now here's where it gets really interesting. Not all alcohols are the same. In fact, they're part of a whole family, and their different personalities all come down to their structure. So first up, you've got your primary alcohols. Think of this as the simplest setup. That special OH group is just hanging out on a carbon atom at the very end of the line. Take a look at butan-1-ol. See how the OH is on that end carbon? That carbon's only attached to one other carbon. And because it's so exposed, just sitting out there on the edge, it makes primary alcohols super reactive and really useful for making other chemicals. Okay, next up we have secondary alcohols. Now the OH group has moved. It's attached to a carbon that's somewhere in the middle of the chain connected to two other carbons. It's a little more crowded in there, which makes it a bit less reactive. And finally, we get to tertiary alcohols. In this case, the OH group is attached to a carbon that's like a major intersection. It's connected to three other carbons. It's so crowded and shielded that the OH group is really well protected, making these alcohols the most stable and the least likely to react with anything. So why do we care about all this? Well, this is the crucial part. Just by changing the location of that one OH group, you create a totally different substance. Propan-1-ol and propan-2-ol had the exact same atoms, but one is a primary alcohol used in industrial solvents, and the other is the secondary alcohol you know as rubbing alcohol. It's a perfect example of how in chemistry, structure is everything. So with all these different arrangements, you can imagine things could get confusing fast. That's why chemists came up with a really clear, logical set of rules for naming them. It's kind of like giving every single molecule its own unique street address. And it might look a little technical, but it's actually super straightforward. First, find your longest carbon chain that has the OH group. Then, you just swap the E at the end of the name for all. After that, you number the chain so the OH group gets the lowest possible number, and you're pretty much done. It's the language chemists use to make sure everyone knows exactly which molecule they're talking about. Now, alcohols don't just exist on their own. They're part of a bigger family tree, and they have some really interesting chemical cousins that are built on very similar ideas. So say hello to the ethers. The easiest way to think about an ether is to imagine two alcohol molecules getting smushed together and spitting out a water molecule. Instead of an OH group on the end, you get an oxygen atom that acts like a bridge between two carbon chains. You've probably heard of ether as an early anesthetic, but these days it's mostly used as a really good solvent.
And now for our second cousin, the thiol. The structure is almost identical to an alcohol, but with one tiny change. You take the oxygen atom in that hydroxyl group and you swap it out for sulfur, its neighbor on the periodic table. And that one simple swap creates a family of compounds that is famous for one thing above all else: its smell. And when I say smell, I mean smell. That sharp, unmistakable scent of garlic? Thiol. A skunk's defensive spray? That's a thiol. Even the foul odor of sewage is thanks to thiols. But this powerful property can actually be a lifesaver. Natural gas has no smell on its own, so utility companies add a tiny, tiny amount of a thiol to it. That way, you can smell a leak immediately and stay safe.
So we've gone all the way from gunpowder tests to garlic and skunks. But what's the big takeaway here? Why does all of this fundamental chemistry actually matter in the real world?
Well, the core idea is pretty simple, but powerful. Tiny changes in a molecule's structure can lead to massive differences in what it does. That little OH group makes alcohols polar, which makes them great solvents. Where you put that group determines if it's an industrial cleaner or a medical antiseptic. And swapping just one atom for another can give you something that smells famously awful or saves your life. This chemistry is everywhere.
So now you know, this elegant, hidden chemistry is all around us. The invisible architect shaping our world. It kind of makes you wonder, what other molecular secrets are hiding in plain sight?